Okay, we're going to start now the second session, and we're starting with Manik Varma, who will talk about the extreme multi-label loss functions, and I hope he will also tell us why he was not happy with Inderjit's talk.
Come for dinner. Thank you so much, Sammy. Right, so I'm Manik Varma from Microsoft Research India, and I'll be talking about extreme multi-label loss functions. This is joint work with my PhD students at IIT Delhi, Himanshu Jain and Yashoteja Prabhu, and our paper appeared earlier at KDD this year. Now, our field has reached a level of maturity where we've identified concrete applications in tagging, ranking, and recommendation, and where we've also come up with some very clever algorithms, such as PD-sparse and DISMEC, which were presented earlier in the workshop, for tackling some of these applications. So at this point of time, I think that perhaps the most important research question that our field needs to address today is, what are good loss functions for extreme classification? In particular, what kinds of losses should algorithms such as PD-sparse and DISMEC be optimizing during training? And perhaps even more importantly, what kinds of loss functions should we be using to evaluate the performance of these algorithms? So I think, like, as academics, how do we decide that we've picked the best algorithm and make sure that the field is making progress, right? So which algorithm is really better, PD-sparse or DISMEC? Right? Or if you were working in a corporation, or if you had formed your own extreme classification startup, which algorithm would you ship to your users? And even if you could choose the right algorithm, how would you tune its hyperparameters? We need good loss functions in order to answer all these questions. And so that is going to be the focus of my talk today, rather than algorithms. I'll touch upon algorithms only towards the fag end when I'm presenting results. Now, the way we evaluate performance must be tied to applications. So the applications that I'll be considering in my talk today include item-to-item recommendation on Amazon, as well as ranking of queries on Bing for advertising. But the application that I will be using as a running example throughout my talk will be tagging on Wikipedia. So the task is very simple. Given a Wikipedia article, we would like to predict which subset of Wikipedia tags might actually be relevant to this article. And to evaluate performance, we'll use the ground truth labels or tags provided by Wikipedia's editors in terms of the tags that they've deemed to be relevant, which I am showing over there for the Divine Comedy. Okay. So a number of loss functions have already been proposed in the traditional multi-label learning literature, ranging from the Hamming loss to the Wasserstein distance. But I think that none of these loss functions are suitable for the extreme setting. Right? In particular, the last time I looked at all the publications in this area, more than half of the papers that had been published on extreme multi-label learning had evaluated the performance of their algorithms using the Hamming loss. And people do similar things in recommendation where they will evaluate using RMSE. Right? But I think the very notion of what constitutes a good prediction changes when you move from dealing with thousands of labels to millions of labels. Right? So I don't think any of these loss functions are very appropriate, but we can follow three very simple design principles in order to adapt some of these loss functions to the extreme setting. And my talk is going to mirror Thorsten's very closely, so please bear with me. So our first design principle is that extreme losses should be computed on the relevant labels alone and should not be influenced by the irrelevant labels. This is because any given data point on average will have only a handful of relevant labels, but millions of irrelevant ones. So it therefore becomes far more important to correctly predict the relevant labels and to ensure that they are highly ranked than it is to predict the irrelevant labels. So for instance, in this example, Wikipedia's editors have provided only 14 tags for the Divine Comedy, so only 14 relevant labels. And so it becomes far more important to predict that a tag such as epic poems in Italian is relevant to the Divine Comedy than it is to predict that an irrelevant tag such as baseball or some random tag such as baseball is irrelevant. Right? So traditional multi-label loss functions, such as the Hamming loss, place an equal emphasis on predicting the liked and the relevant and the irrelevant labels. Right? And so our first, and they also have no concept of ranking built into them. So our first recommendation is to switch away from the Hamming loss in favor of ranking losses defined on the relevant labels alone, such as precision at k and nDCG at k. However, it is not sufficient to just switch to precision or nDCG or any other loss defined on the relevant labels alone, because as Thorsten pointed out, many relevant labels are actually missing. So the paradigm in traditional supervised learning is to take a data point, give it to some human experts, and have them annotate it, and now you're ready to do training and testing, right? But this technique simply doesn't work in the extreme setting, because no human being can go through a list of 1 million labels and mark out the exact relevant subset. And so irrelevant, missing labels will abound, right? So if you look at this example, even though Wikipedia's editors did a very good job in marking out the relevant tags for the Divine Comedy, they still missed out many relevant tags such as Dante Alighieri, visionary literature, allegory, medieval philosophical literature, and so on. Traditional ranking losses, such as precision and nDCG, will actually penalize you for predicting these missing labels, for predicting that Dante Alighieri is relevant to the Divine Comedy, and will therefore provide you a biased estimate of the true loss computed on the full ground truth. So our second design principle is that extreme losses computed on the observed ground truth, where labels go missing with under arbitrary probabilistic label noise models, should nevertheless provide an unbiased estimate of the true loss computed on the full ground truth. And as Thorsten had done earlier, we will be introducing propensity scored losses, such as propensity scored precision and propensity scored nDCG, in order to achieve this goal. Our final design principle is that depending on the application, extreme losses should place more emphasis on tail labels than head labels. So it turns out that in the extreme setting, labels do not occur with uniform probabilities, but rather they follow a power law distribution. This means that there will be lots and lots of labels which occur very infrequently, have very little training data, and are therefore very hard to predict accurately. But at the same time, they might be much more rewarding or much more informative if you predict them correctly as compared to generic head labels or popular labels. Right? So for instance, on Wikipedia, almost 250,000 tags occur in less than 5 articles each. Right? And if you look at a tag such as 1321 books, it occurs in only 3 Wikipedia articles. Right? So if there were only 3 or about only 3 major books that were published in 1321, and you predict that the Divine Comedy is one of them, this is way more informative than predicting that some popular or generic tag such as books or poems is relevant. Right? That might be applicable to many thousands of articles on Wikipedia. So traditional ranking losses, including precision and nDCG, do not distinguish between head and tail labels. But the propensity models that we'll be developing will naturally promote the accurate prediction of tail labels and the recommendation of rare items. In fact, we'll show that this provides a sound theoretical justification for some of the very popular label weighting heuristics that people have developed in the recommender systems literature for recommending rare items that will delight and surprise the user. Okay. So for the remainder of the talk, I'm going to be focusing on developing propensity scored loss functions and propensity models. And I'll be using the language of recommendation to drive home the point. So I'll be talking about users and items and likes. So to map that onto Wikipedia, a user is a Wikipedia article, an item is a Wikipedia tag, and a like means that that tag is relevant to the Wikipedia article. Okay? So suppose that our task is to evaluate the performance of a silly constant recommender which always recommends apples and bananas to all its users. Furthermore, suppose that somehow by magic we've obtained Y star, which is the complete ground truth information about which user likes which items, with no missing labels. Right? Then, as you can see in this case, the true precision at 2 will simply turn out to be 1. Right? It'll be perfect because all the users actually do like apples and bananas. But obviously, obtaining Y star is impossible. So suppose what we had really obtained was Y, which is the observed ground truth information, where 50% of the labels from Y star have gone missing uniformly at random. Okay. Then in this case, you can see that the observed precision at 2 will fall down to 1/2, And that's because we'll think that the first and third users didn't really like apples and bananas, and the second and fourth users didn't like apples, and so that these recommendations were poor. Right? So we'll be getting a biased estimate of the loss. However, we can do something very simple, as Thorsten was saying, 3 lines of math, to actually unbias this or debias this setting. And all we're going to do is simply assign a weight of 2 to each correct prediction. Right? And if you do this, lo and behold, your observed precision will again become unbiased. You'll get back 1. So the intuition is very simple. You should count all your correct predictions just as you would normally have done if you were calculating your vanilla precision. But then you simply double your count because you know that half the ground truth has gone missing and only half of your predictions were counted correctly. Okay? So the situation where labels go missing uniformly at random is somewhat uninteresting, I think. And that's because the unbiased precision turns out to be exactly the same as the biased precision, but just multiplied by a global constant. So if you had 3 algorithms whose biased precision was 1 by 2, 1 by 3, and 1 by 4, then their unbiased precisions would turn out to be 2 by 2, 2 by 3, and 2 by 4, and there would be no change in the relative ordering of the algorithms. Right? So in this case, we could just as well have used the biased precision to figure out which was the best algorithm and to ship that into production. And we know that that doesn't work. So unfortunately, most of the work that has happened in the missing labels literature and the recommender systems community is all on when labels go missing uniformly at random. But the propensity scoring techniques that have been developed actually apply even when labels go missing under arbitrary probabilistic label noise models. So the way I'll define the propensity PIL is the probability that a relevant label a label L, which is relevant to document I, is retained in the observed ground truth. So it doesn't go missing. Right? So PIL is the probability that YIL is equal to 1, given that Y star IL is equal to 1, where Y star is the full ground truth, Y is the observed ground truth, and 1 means that the label is relevant to the document. Okay? So this definition of propensity is slightly different from the standard definition that Thorsten used earlier. But using this definition, we can prove that if you assign a weight of 1 by PIL to every correct prediction, you'll get an unbiased estimate of your true loss. Okay? Now, note that this result is true only in expectation, and that our evaluation could be wildly inaccurate for any individual user, as it is the case over here for user 3. So for her, we predict that her precision is 0, whereas it actually should be 1. So here's a formal statement of our theorem, and all it essentially states is that if you take the propensity scored loss, which is nothing but the original loss weighted with the inverse propensity 1 by PIL for user I and item L, then this computed in expectation over the observed ground truth will give you an unbiased estimate of the true loss computed over the full ground truth. And of course, as with any theorem, we had to make some assumptions in order to get here, but these assumptions are fairly mild. So the first assumption is that the loss function should decompose over the individual labels, which is certainly the case for precision and nDCG. The second assumption is that only relevant labels should contribute to the loss and irrelevant labels should not matter. And that is again true for precision and nDCG by definition. And our third assumption is that the label noise should be one-sided, which is to say that while relevant labels might go missing from the observed ground truth, but irrelevant labels can never appear. And this is again true for applications such as Wikipedia, because the editors are not malicious and irrelevant tags will never appear. I mean, if they appear, the editors will weed them out. But this might not be true for situations when we are harvesting our labels from, let's say, our click logs or automatically in some other way. So, but it turns out that empirically, things still seem to work fine even in that setting, right? Okay, so this is the setting for precision and nDCG. But it turns out that there are also many other loss functions. Excuse me. There are many other loss. Can I have a water, please? There's some in my bag. There's a bottle. Kunal, if you could just hand me. Cheers. Sorry about that. Excuse me. Where? Oh, fantastic. Thank you. Sorry. So as I was saying, there are many other loss functions, such as recall, the mean reciprocal rank, average discounted gain, and the F score, where the loss function is actually not decomposable. So for such losses, we have an equivalent theorem which states exactly the same thing, but needs to make one extra assumption, which is that the probability distribution over the complete ground truth is a delta function. Okay? So I'm going to skip over the concentration bounds in the interest of time. All I'd like to point out is it has the usual properties that as the sample size increases, the bias decreases, and the bias will ultimately go to 0. And the other good thing is that it does not depend on the total number of labels that you have in your problem or in your application, but just on the active number of labels, which might be far lower, right? Yeah. So I think the final question that, or the one big question that remains after we do this is, where are these propensities going to come from? Now, as Thorsten mentioned, this is an open research challenge, problem. And the first solution that we attempted is to propose a parametric sigmoidal model on a semi-log scale. So given a label L, which occurs NL times in the observed ground truth, its propensity PL can be modeled as a sigmoidal function of log NL with two dataset dependent hyperparameters A and B, and a constant C which gets frozen the moment you fix A and B. So this model was born out of two observations. The first is that tail labels tend to go missing more frequently as compared to head labels. And that's because there are just so many of them, right? You tend to forget them very easily. The second observation is empirical. So it turns out that on applications such as Wikipedia and Amazon, there exists extra information or metadata which you can use to estimate these propensities. So for instance, Wikipedia provides a hierarchy over its tags. And if a tag is relevant to a particular article, the hierarchy implies that all ancestor tags must also be relevant. So we can use this fact to get a first order approximation of which labels are missing on which documents in Wikipedia, and we can estimate propensities. And you can see that our proposed model gives a reasonable fit to Wikipedia in this case. We can do a similar thing for Amazon. And again, I'm not going to go into details because of the interest of time, but you can see that our fit is even better in this case. Okay. So finally, let me also just briefly discuss how our propensity model helps in recommending rare items. So if you recall, propensity scoring essentially just adds a weight to every term in your loss function. The weight is 1 by PIL. And because precision and nDCG are linear in our case, this weight 1 by PIL can be pulled into the loss function. So the propensity scored loss is identical to the original loss, where the original loss has the ground truth labels have been weighted by 1 by PIL. It's as simple as that. So if you look at this plot, and you look at the weights, then you can see that the tail labels which are on the left receive far larger weights than the head labels which are on the right. So our model naturally learns to assign higher rewards to tail labels if we predict them accurately, or if we recommend rare items. Now, while I'm not aware of propensity scoring having been used in the recommender systems literature, or in this particular setting, label weighting has certainly been very popular in the recommender systems community. So various heuristics have been proposed, including weighting the ground truth labels by log n by NL from an information theoretic point of view, or NL to the power minus beta, and so on. And while you can see that there is some similarity with the weights that we've proposed, which are 1 by PIL, there are also some differences, right? So actually our weights match log n by NL on the tail, but match NL to the power minus beta on the head, right? So you can think of our model as providing a sound theoretical justification for some of these label weighting heuristics that have become very popular in the literature, but where we provide a more principled setting of the weights, because those weights, you might not even recover valid probabilities from them. Okay. So finally, on to algorithms, and I'll spend only a minute over here. So given our propensity scored losses, you could have plugged them into any algorithm that you like, right? PD sparse, DisMEC. But we plug them into FastXML because it already optimizes nDCG. And in order to optimize propensity scored nDCG, we didn't have to change a single line of code. As I mentioned earlier, all you need to do is reweight your ground truth labels by 1 by PIL, and the job is done. So that gives us propensity scored FastXML, or PfastXML. And then we add a tiny re-ranker on top of that, which we can train in milliseconds, and which also makes predictions in milliseconds. And so you get propensity scored re-ranked FastXML, that's faster XML. And again, the re-ranker is not all that important. Again, if you had more budget, you could have used PD sparse or DisMec or whatever you like. So let's quickly look at some results. So the first experiment that we performed is to test whether propensity scored nDCG really is unbiased. Right? So we took the EUR-Lex data set, and we simply assumed that we have the complete ground truth information available on that data set. So we trained FastXML on the training set, made it predict on the test set, and then froze all the predictions. Okay? So that gives us the true nDCG, which you can see at the top as a faint red line, which is somewhere about 65%, so it's a constant horizontal. Okay? Then we started simulating missing labels from the test set, and we dropped labels. And as you can see, the observed nDCG keeps falling down as we get more and more missing labels. Now, even though FastXML's predictions have been frozen, they're not changing. It seems that the performance seems to get worse and worse, right? And this shows that there's a clear bias in vanilla nDCG. But if you were to now compute propensity scored precision on these same missing labels, that's the curve at the very top, you can see that the first thing is it's almost identical to the nDCG curve. It's a very little difference. It's almost unbiased. And it's also pretty stable as labels go missing. So this shows that propensity scoring really does work. And propensity scored nDCG can give you an unbiased estimate of the true loss. So well, if propensity scoring really does work, how do all the algorithms stack up for propensity scored nDCG? So this is the EUR-Lex data set. We took a lot of algorithms and measured their performance. And so in response to the question, which algorithm is better, PD sparse or DisMec, the answer is obviously faster XML. So the results actually get interesting if you go start looking at them in depth, right? So here's the Amazon cat data set. And if you just look at vanilla nDCG, it will tell you that both FastXML and faster XML, there's nothing to choose from between them. They give the same performance, exactly the same. Sleek and DisMec are slightly lower over here. But if you look at propensity scored nDCG, it appears that there's a 20% difference in performance between FastXML and faster XML. Faster XML is better by 20%. So what really is going on? The answer is provided by the two plots that you see below. So the plot on the left is plotting which labels are each of the algorithms getting correct. Right? And the tail labels are on the left and the head labels are on the right. That's the standard convention. And if you look at FastXML, you can see that it's focusing all its attention on the head labels. Okay? So if you look at the million test points that there are on Amazon Cat, then if you look at FastXML's top ranked prediction,
1 minute.
I see, okay, almost done. So it gets only 266 predictions, it predicts only 266 unique labels out of a total of 13,000, right? And so its coverage is really poor. Whereas faster XML does the entire tail. You can see it's making predictions on the tail, and it predicts more than 10,000 labels out of 13,000, right? So I'm almost out of time, so I'll skip Wikipedia because that's already been presented before. I'll skip Amazon and Bing also. The only thing I'd like to mention is that faster XML can scale to about 10 million labels on a very small server. So I think that's really important in terms of training. And the prediction time is just 1 or 2 milliseconds, which is really important if you want to deploy into production. So again, I'm going to skip all the results because I'm out of time. I wanted to show you some qualitative examples of what prediction on Wikipedia already looks like. I'll just mention that faster XML will get rare tags like 1321 books, epic poems in Italian, etc. Skip over all of this. Just mention that Bing, again, so I'm completely out of time. But so I'll just mention briefly that faster XML is actually now deployed in Bing. It's running on 100% traffic in many multiple markets around the world. And not only is it improving CTR, like the click-through rate, but it is also improving coverage in advertisers. So ads that had never been shown before on Bing are now being shown because of fast XML. Okay? So again, please come and talk to me later on if you want details. I'll have to skip all of this. So just to conclude, I have only 2 take-home messages for you. The first is that if you're going to do research in this area, I would request you to try and adopt propensity scored loss functions, move away from the Hamming loss, and try and use propensity scored precision or nDCG. You would be a much happier person yourself in the end. The other point is that the code for PfastreXML is available from the Extreme Classification repository and on my website, and you can use it to train on very large problems. Thank you very much.
We have time for a few questions. Yes.
Is that John Langford?
Yeah, it's John.
Hey.
So there's the loss function that you use when you're in a supervised regime, but then when you're in a live regime, you have feedback about what was actually chosen or by a user or clicked on or what revenue you got or things like this. And I guess what I'm wondering is, so the way I'm thinking about this is that you're trying to create an offline loss function, which is going to be somewhat closer to what you get in the actual feedback regime. But I'm wondering if you have a deeper thought about that?
Right. So there are 2 responses here. The first thing is that we can't flight everything, right? Ultimately, it would be good to flight everything, but it's just so expensive that we can't, right? So if you have offline situations where you have 3 algorithms and you're looking which one should I flight, how should I set the hyperparameters for these? Should I have 10 trees, 50 trees? What features should I use? Some of these things have to be done offline. And so for that, we need something which correlates well with our online flight metrics. So that was the problem that really motivated me. The second thing is when you get online, then you, Thorsten, you've all been doing this work on bandit feedback and counterfactual stuff, right? And I haven't managed to wrap my head around that. And how exactly is that related to what I've been doing over here? So it'd be very good to sit down and try and understand that in more detail. Where I am going is trying to see if we can run, so if I can do exploration, right? If I can actually get feedback and do exploration, I can get data from that to design better propensity models. How would that fit with what you guys have been doing with your bandit feedback stuff? I think that it would be good to actually discuss that.
One last question, quickly.
So I found it interesting in the plots you have about PfastreXML and what labels predict. It tends to predict some of the very rare labels and then nothing in the middle and then a lot of the big labels, of the sort of very common labels. Am I interpreting correctly?
No, so I think what happens on Wikipedia, so at least in this Wikipedia case, is that you have a few head labels and then it suddenly plummets the distribution and then everything is more or less the tail. So I think the reason why you're not seeing a torso is because it just doesn't exist on Wikipedia. In other cases...
I meant another. Can you go 2 slides back?
Oh, I'm so sorry. I can't see my
1,
slides.
2, 3. Here, for example.
Yeah.
Right. So if I interpret correctly, you have a lot of sort of rare labels that are predicted, and then nothing in the middle, and then the common labels you predict them again.
Yeah. So I need to check what's happening over there. Even things like DisMec all of us, Sleek, PfastreXML, DisMec, we all seem to follow the same trends.
Yeah, and
the
previous slide
middle
was
is flat.
Previous slide was even more. Here, for example, I have some rare labels and then nothing in the middle, and then you jump up again.
Right.
I was wondering if you have an explanation for that.
Yeah, no, we need to go and look at that in more detail. It could also be because you get more reward for going towards the tail. So if you can get that right, you should try and push as much over there. So maybe I think that might be one of the explanations. But yeah, we need to go and have a deeper look.
Thanks.
Okay.
Thank you.
Let's thank Manik again.